Hello everyone. In this session, we are going to have a small discussion on an introduction to power electronics. The demand for control of electric power for electric motor drive systems and industrial controls existed for many years, and this led to early development of Ward-Leonard system to obtain a variable DC voltage for the control of DC motor drives. Power electronics have revolutionized the concept of power control for power conversion and for control of electrical motor drives. Power electronics combines power, electronics, and control. Control deals with the steady state and dynamic characteristics of closed loop systems. Power deals with the static and rotating power equipment for the generation, transmission, and distribution of electric power. And finally, electronics deals with the solid state devices and circuits for signal processing to meet the desired control objectives. Therefore, power electronics may be defined as an application of solid state electronics for the control and conversion of electric power. Power electronics is based primarily on the switching of power semiconductor devices. With the development of power semiconductor technology, the power handling capabilities and the switching speed of the power devices have improved tremendously. The development of microprocessor or microcontroller technology has a great impact on the control and synthesizing the control strategy for power semiconductor devices. Power electronics have already found an important place in modern technology and are now used in a great variety of high power products, including heat controls, light controls, motor controls, power supplies, vehicle propulsion systems, and high voltage direct current HVDC, as we commonly call it as, systems. It is difficult to draw the boundaries for the applications of power electronics, especially with the present trends in the development of power devices and microprocessors. The upper limit is undefined. Now, let us have a small look at the brief history of power electronics. The first power electronic device developed was the mercury arc rectifier during the year 1900. Then the other power devices like metal tank rectifier, grid controlled vacuum tube rectifier, ignitron, fanotron, thyratron, and magnetic amplifier were developed and used gradually for power control applications until 1950. The first SCR or Thyristor was invented and developed by Bell Labs in 1956, which was the first PNPN triggering transistor. The second electronic revolution began in the year 1958 with the development of the commercial grade thyristor by the General Electric Company. Thus, the new era of power electronics was born. After that, many different types of power semiconductor devices and power conversion techniques have been introduced. The power electronic revolution is giving us the ability to convert, shape, and control large amounts of power. There are boundless applications for power electronics. Here we have listed a few just for your reference. For example, in commercial applications, power electronics is used in heating systems, ventilating, air conditioners, centralized refrigeration, UPS, and so on. So, in domestic applications, you have cooking equipments, lighting, heating, air conditioners, refrigerators, and features. Once again, in the industrial applications, we have pumps, compressors, blowers and fans, machine tools, etc. etc. In the aerospace applications, we have the space shuttle power supply systems, satellite power supply systems, aircraft power supply systems. In the telecommunication, we have the battery chargers, power supplies, mobile cell phone battery chargers. And finally, in the transportation, you have the traction control of electrical vehicles, battery chargers for electric vehicles, electric locomotives, and etc. Right, with this brief introduction to power electronics, we come to one of the most important topics, which is the power semiconductor devices. Since the first thyristor of silicon controlled rectifier was developed in late 1957, there have been tremendous advances in the power semiconductor devices. Until 1970, the conventional thyristors had been exclusively used for power control in industrial applications. Since 1970, various types of power semiconductor devices were developed and became commercially available. Hence, the power semiconductor devices are broadly categorized into three types, as we can see in the diagram here. First, we have the diodes, then we have the thyristors, and lastly, transistors. Now, the diodes are basically further categorized into general purpose diodes, high speed diodes, and finally Schottky diodes. Thyristors have multiple types. We have the most basic, the silicon controlled rectifier. Then we have the GTOs, which is the gate turn off thyristor. Then we have reverse conducting thyristor called as RCTs, static induction thyristors represented by SITH, gate assisted turn off thyristors GATT, light as LASER. So we have uh, the light activated silicon controlled rectifier, which is LASER. Then we have the MCT, mass controlled, and finally track. Coming to the transistors, we have the bipolar junction transistors, we have the MOSFETs, then we have a combination of BJT and MOSFET, which is called as the IGBT, and which stands for insulated gate bipolar transistor, and finally we have static induction transistors also. Right, now with that, let us discuss each of them in a little bit of a detail. So I'll start with power diodes. Power diodes are made of silicon PN junction with two terminals called as anode and cathode. The diode is said to be forward biased when anode is made positive with respect to the cathode. It conducts fully when the diode voltage is more than the threshold voltage, which is 0.7 for silicon and 0.3 for germanium. And the conducting diode will have a very small voltage drop across it, which is equivalent to the threshold voltage of the corresponding device. Further, the diode is said to be reverse biased when the cathode is made positive with respect to the anode, and when under reverse bias condition, a small reverse current known as the leakage current flows and the diode is said to be in the off state. This leakage current increases with the increase in the magnitude of the reverse voltage until the avalanche voltage is reached, at which the diode breaks down. Now going to the categorization of the diodes. Now, before that, let me show the simple VI characteristics of the diode. You can see it only takes a small voltage to trigger or to turn on, which is equal to the threshold voltage. After that, the diode current rises exponentially. Whereas in the reverse biased condition, the diode takes a large voltage called as the breakdown voltage, and at which voltage the avalanche breakdown occurs and a large reverse current will also flow across the device. Now coming to the categorization of the power diodes, as we already have said, we have three particular types: general purpose diodes, then we have the high speed, also called as the fast recovery diodes, and finally Schottky diodes. General purpose diodes are available up to 3000 volts, 3500 amperes, and the rating of fast recovery diodes can go up to 3000 volts and 1000 amperes. The reverse recovery time varies between 0.1 and 5 microseconds. The fast recovery diodes are essential for high frequency switching of power converters. A diode, usually as we already have seen, will have two diodes, a cathode and an anode, whereas a Schottky diode have low on-state voltage and very small recovery time, typically in the order of nanoseconds. The leakage current increases with the voltage ratings, and the ratings are limited to 100 volt and 300 amperes. A diode conducts when it is, as we have said, anode is at a higher potential with respect to the cathode, and this condition is also called as the forward biased condition. If the cathode voltage is higher than its anode voltage, it will go into the blocking mode, which is the reverse biased condition. Uh, we probably have a small diagram for the Schottky diodes here. You can see one of the interesting feature of a Schottky diode is that one part of the Schottky diode is made up of semiconductor, where the other part is made up of metal. So this is a small introduction to diodes, power diodes. Now coming to the thyristors, very importantly, a thyristor has three terminals: anode, cathode, and gate. By the look of the diagram, you might understand it looks very similar to that of a diode, except that now it has an extra terminal called as the gate terminal. This also is sometimes called as the control terminal of a diode. When a small current is passed through the gate terminal to cathode, with respect to cathode, the thyristor conducts, provided that the anode terminal is at a higher potential with respect to the cathode terminal. Once a thyristor is in a conduction mode, The gate circuit has no control and the thyristor continues to conduct. This operation is also called as latching. When a thyristor is in the conduction mode, the forward voltage drop is very small, typically equal to the threshold voltage, which is equal to 0.5 to 2 volts. A conducting thyristor can be turned off by making the potential of the anode equal to or less than the cathode potential, at which state the current voltage drop across the device will go zero and the current will cease to zero, and that is how the device stops conducting. The line commutated thyristors are turned off due to the sinusoidal nature of the input voltage, and forced commutated thyristors are turned off by an extra circuitry called the commutation circuitry. And when I say line commutated, you must understand the type of the input voltage source is AC, and when I say forced commutation, you should remember the type of the input voltage source is DC. So here you can also see a structure of a thyristor. So this we have, it is a PN-PN structure. Compulsorily the P type or the P side must be the anode and the N type must be the cathode. And the second layer from the cathode is usually represented by the gate. So from the anode towards the cathode, you can say, since we have 4 layers, you will have 3 junctions. We'll name them as J1, J2 and J3, and depending upon what voltage is applied, 2 or one of the junctions will forward bias and the other one will reverse bias, and by the application of gate you can forward bias the remaining junction also. Right. So as we already have seen, thyristors can be subdivided into different types. So we have forced commutated thyristors which come under the inverter grade. Then we have the line commutated thyristors which come under the converter grade. So an inverter, as we know, converts DC to AC. A converter converts AC to DC. So this is what actually is the basic categorization of a thyristor. Further, we have the gate turn off thyristor. So in the previous one we said gate has no control once the thyristor is turned on. This is the basic characteristic of a thyristor. However, there are other types of thyristors in which you can apply a negative voltage to the gate terminal and turn off the thyristor. So such thyristors are called as GTOs. Then you have the reverse conducting thyristors which will conduct in the reverse direction. Then we have the static induction, gate assisted turn off, light activated SCR, and finally MOS controlled thyristors. Right, let us have a little more discussion on the thyristor types here. Let us start with the line commutated, or also called as the natural thyristors. Let us start. Yeah, natural or line commutated thyristors are available with ratings up to 2500 volt and 4000 amperes. The turn-off time of high-speed reverse blocking thyristors have been improved substantially, and it is possible to have 10 to 20 microseconds in a 1200 volt 2000 ampere thyristor. The turn-off time of a thyristor is usually defined as the time interval between the instant when the principal current has decreased to zero after external switching of the principal voltage circuit and the instant when the thyristor is capable of supporting a specified principal voltage without turning on. It is very important. Now, we have also seen RCTs and GATTs, which is reverse conducting and gate assisted. So, they are widely used for high speed switching, especially in traction applications. An RCT can be considered as a thyristor with an inverse parallel diode. RCTs are available once again up to 2500 volt, 1000 amperes with a switching time of up to 40 microseconds. On the other hand, GATTs are available up to 1200 volt and 400 amperes with a switching speed of around 8 microseconds. LASCRs are available up to 6000 volt 1500 amperes with a switching speed of 200 to 400 microseconds, and they are suitable for high voltage power systems, especially in HVDC. For low power AC applications, triacs are widely used in all types of simple heat controls, light control, motor control, and AC switches. So the characteristics of triacs are similar to two thyristors connected in inverse parallel and having only one gate terminal. We will see the symbol and the working of a thyristor probably in the next topic. The current flow through a thyristor should be noted can be controlled in both directions. It is a bidirectional device, whereas an SCR is an unidirectional device. So you can see for a thyristor, the current flows only from anode to cathode, whereas for a for a triac, it can travel in both directions. Right, now coming to the GTOs. GTOs and SITH, static induction thyristors, are self-turn-off thyristors. GTOs and SITHs are turned on by applying a short positive pulse to the gates and are turned off by the application of short negative pulses to the gates. It is one of the interesting characteristic of these devices. They do not require any commutation circuit, and GTOs are very attractive for forced commutation of converters and are available up to 2500 volt and 1000 amperes. On the other hand, SITH, static induction thyristors, are expected to be applied for medium power converters with a frequency of several hundred kilohertz and beyond the frequency range of GTOs. So that is about the thyristors. Finally, we have the last categorization, which is the transistors. Again, these are power transistors, not to be confused with the low voltage transistors. Right. High power bipolar transistors are commonly used in power converters at a frequency below 10 kHz and are effectively applied in the power ratings up to 100 kilowatt and 1000 volt. A bipolar transistor, as we all know, has three terminals and they are called as emitter, base and collector. It is normally operated as a switch in the common emitter configuration as long as the base of the NPN transistor is at a higher potential than the emitter and the base current is sufficiently large to drive the transistor in the saturation region. The transistor remains in the on state provided that the collector to emitter junction is properly biased. The forward voltage drop of a conducting transistor is in the range of 0.5 to 1.5 volts. If the base drive voltage is withdrawn, the transistor remains in the non-conduction mode. Power MOSFETs are very similar to BJTs in the way of operation and are basically used in high-speed power converters and are available at a relatively lower power rating in the range of 1000 volts. 1000 volts, 50 amperes, and at a frequency range of several tens of kilohertz. So basically, power MOSFETs are faster compared to power transistors. The ratings of commercially available power semiconductor devices, probably you can obtain them at whenever you buy or purchase a particular device, you will always get a data sheet at which you will probably given all the values of what is the maximum voltage you can apply, what is the maximum frequency of application the device will be suitable for, and so on. So that is about the power transistors. Probably we'll have to give a small emphasis on IGBTs as well. So an IGBT, as we can see here, is an insulated gate bipolar transistor. So by default it is a bipolar transistor, which is a BJT. But it also derives some of the positive characteristics of the MOSFETs, and that is why it is called as insulated gate. So when you look into the connections or the terminals of an IGBT, it has two terminals derived from BJT, which are emitter and collector, and it has the control terminal derived from the MOSFET. So it has gate, emitter and collector, and it borrows only the positive traits from both both BJT as well as MOSFET. Right. With that, we will end this session, and in the next session, probably we will go into the control characteristics of different power devices. Thank you.